Welcome to Advanced Data Analysis 1 with me, Erik, Erhardt, Professor of Statistics at the University of New Mexico. In this video, I hope get you started with using logistic regression for prediction. So we'll download the worksheets in our class folder for this, the QMD and the data. Now, it's possible that we've already downloaded this data in a previous assignment. So if you do have to, either override it or don't download it again, or but don't let your system change the file name on you, like with a parenthesis 1 or something. All right, we need to go to that folder and choose the file and set the working directory session, set working directory to source file location, and render it. This is a cool assignment. A lot of new ideas here, different from the rest of the course. When you're doing prediction, you want to know how accurate you are. And you might have multiple competing models to predict the same thing, and you might want to do some comparison about which models do the best prediction. So the modeling in this assignment I do for you, and all of the questions are about understanding and interpreting the data or the predictions, the quality of predictions, and ultimately making a decision about which model you would prefer for making the predictions. So we are going to use some of that data that we had from a previous year where we measured the hand span and the height of people in my class, and we also recorded their gender, and there may have been something else I forget. But those are the variables that we're going to use. Okay, so we record the height in inches, we record the hand span in centimeters. This is just to make the point that correlation is a unitless measurement, and it doesn't actually matter what units you measure in. And we are going to, oh, you know what? You don't have to choose anything. In fact, this title may be different by the time you get here. But I'm going to fit two models, one that predicts sex or gender from hand span, and the second will predict gender from height. Okay, so if, for example, if you saw a silhouette of someone and you only saw their height, could you use that information to predict whether that person is male or female? Okay. Similarly, now this is less likely, if you had the hand span of someone that you measured from thumb to pinky, if you saw something like that, that they had their hand, printed on a piece of glass or something, so you saw the oil on there, like fingerprints, could you determine if that's a male or female from that? Okay, so probably if you measure enough physical, secondary sex characteristics, the morphology of your body, probably you could figure out male or female. After all, that's how we identify quite naturally what sex people are when we look at them. The shape of their chin, all that sort of stuff. So what I've done here, so I'm going to talk you through some of the code so we can understand how this was done, but it's not really critical that you understand all this because I've done it for you. But basically we have our response variable is going to be sex. In here I'm going to code females as the success variable as a 1, and males as the failure variable or 0, right? These are just labels to indicate, a 1 or a 0 on the response scale for the Bernoulli, right? These are based on Bernoulli trials. Bernoulli trials are success and failure, like flipping a coin. Do you get a head or a tail? You call the outcome that you are interested in, you call a success, and everything else is a failure, okay? But it doesn't actually mean success and failure, right? Those are just labels. I probably don't need to be quite so apologetic about the language used for these things. Okay, and then I've got an x variable, which will either be hand span or height. So here is a switch for either hand span or height. I'm going to save all of the results, all of the data and the results into this dat hand list, and I'm going to populate that list with all the objects that we need. Okay, so for I is going to be our index for the x variable, and it's going to be 1 and 2, and it's going to go along this list of hand span, or this switch hand or height, right? So the sequence along this list is going to be a 1 for hand and a 2 for height. So the first time through the for loop, Ix is going to be a 1. It's going to do all the stuff related to hand, and then the second time through it's going to be a number 2, and it's going to do everything related to height. So the first thing I do is make a sublist numbered 1 the first time, and then I'll be able to put everything in there. So in this sublist, first I'm going to store the data. So I'm going to read the data set. I'm going to drop any missing values because I set up the spreadsheet originally to have a row for every possible seat in the classroom. So there's like 14 tables, I think, each with 9 seats. So I had rows for that many people. But a lot of those are empty because I didn't, even if you have 100 people, you still don't fill all the seats. And then we're going to make sure that gender is a factor variable. Because the variable name is gender MF, I'm going to have the M as the first level and F as the second level. And then year is not important, but I turn it into a factor variable. We're not doing any analysis by year. We're using all of data from all the years together. Then we're going to mutate and create the X variable. So the case when is a bit like an if statement. If the height hand variable, if Ix is the first, is number 1 right now. So the first of that, if the first of that equals hand, which it does, then hand span, that column in the data set, is going to be copied to the X variable. On the second time through, Ix is going to be equal to 2, and that's, so the second index of this will give you height. And so in that case, height in inches is going to be copied to the X variable. Otherwise, it's going to, so if it gets past these, if this is false, then the last one is true, then NA is going to be copied to X. So we'll know if we get something wrong because our X variable will be all NAs. So we've created the X variable, and then we need to create the response variable. So if it is a female, it's going to be equal to 1. If it's a male, it's going to be equal to 0. And if it's neither of those two things, then we'll just set it to NA, because those are the two things it should be. So now we've created our X variable and our response variable, and we can use those generically in fitting the model, right? So this is one strategy for iterating through multiple X variables, potentially through multiple Y variables, response variables, by manually setting certain variables to a generic letter, okay, or a generic variable name. Now, I've got a label for the x-axis. So same case when, so this x label is going to be either hand span or height, depending on that same switch. I've got this data summary where for the data set, I start with the data set, I group by the x variable, and then I summarize the number of successes and the number of total, and I calculate these proportions. And we're going to use some of this in some plots. Okay. Finally, we're going to fit the generalized linear model. That is going to be our logistic regression. It's logistic because the family equals binomial. We have the response as a function of x, and we're going to use the data set for, either number 1 for hand, number 2 for height. Okay, and we're going to save that as the GLM. F is female versus the X variable. We're going to make some predictions. So for all the observations, we're going to predict the data and see what the predictions are. These are going to be so-called internal predictions or in-bag predictions. It is better to do external cross-validation, and I'm not getting that deep in this video. I'm just going to show you the basic ideas of using prediction. Okay. The last part is calculating some additional variables in the data set based on our model fit. So we're going to create variables. The fit on the Logit scale, this comes from the fitted values that we, our model predictions up here. We've got our fitted value, we've got the standard error of the fits. We can therefore calculate lower and upper bounds, so we can have these confidence bands around our regression line. And we can use all of those, at least the Logit, we can undo the Logit transformation, called the logistic transformation, to get our proportions P, and we can do the same transformation to get our lower and upper bounds on the probability scale. So now we'll have nice plots. We get to the end of our for loop, we go back to the top, and we do all of it again, where IX increments to number 2, and now we do the data and the model fit for height. Okay, so here's a little bit of output from that. Anyway, each time it reads the data, we get some output. All right, now we're going to plot the data, and all this is just like a big plot with these summaries and probability confidence bands and the proportions, and we're putting some labels on here, labeling the x-axis, etc. And we do that twice, and we put it all together and make this plot. Okay. Whew. We're 12 minutes in and just been doing a lot of narration. Here's the data. Okay. On the left, in fact, on the left we have handspan on the x-axis, and we have the probability of being female on the y-axis. The green dots are down here at 0 for males, so those are the observed handspans for males. For females, there are 1, so these are the observed handspans for females. The black circles are the proportion of females for a given handspan. Okay, so interesting. So yeah, these were measured in millimeters, so there should be about 20 values between 20 and 22. And for any of these that are unique, you see that there's actually some big ones here, definitely on like 21 centimeters exactly, on 20 centimeters exactly, on 19 centimeters exactly. That's because people were round when they'd measure, right? So they put their hand on the piece of paper and they looked at it, and rather than doing, 21.1 centimeters, they just rounded down to 21 centimeters even, right? So we see, like, and you can see these smaller circles down here and up here are like singletons, like a unique person had whatever it was, 21.4 or something centimeters, rather than exactly, this is 21.5. People rounded. So be aware that the data that you get when people measure, or at least if you ask someone to self-measure, that those measurements are going to have some bias. They often do some rounding. For people's heights on dating sites, they often round up, and not necessarily to the nearest inch, but to 1 or 2 beyond that. That sort of deception. Anyway, so that is the pattern for handspan. This curve ideally would follow all these black circles, but a lot of these black circles are singles, like only one person had a specific handspan. So I wouldn't worry too much about the curve going through the black dots. Basically, the pattern we see is that it's close. It should be, the blue line is trying to get closest to all these green dots. It's trying to be high for these, and it's trying to be low for these. And because females have smaller hands than males, it is roughly, in the right place at the right time, right? Very good. Same thing for height. Male heights, female heights. Females are shorter than males on average. Lots of females and males have the same heights. That's this sort of zone of confusion but sort of the max height for females is roughly about 71 or 72 inches, right? 72 would be 6 feet. We have some males up there, but no females. We do have a short male down here at 61 inches, which is 5'1", and we have a couple females down there. But okay, so now the question is, which of these two models will give us a better prediction for whether or not someone is female versus male? Okay, so that brings us to calculating something called the confusion matrix, and we're going to learn now a bunch of terminology. So we'll learn the definitions, we'll apply those to the problem, and that's the rest of the assignment. So the next part is using the function that I wrote to do prediction. This is going to plot an ROC curve. That does a few things. It calculates this confusion matrix, and it also makes a plot that we end up plotting in a moment. So here's a confusion matrix. We're going to look at this table in a moment and a lot of these statistics. This is the set for handspan. I'm delimiting this. You can see print all those lines. I print out the X label, which is this. I print out the confusion matrix, which is all of this stuff. And then I print a couple blank lines. And then these are all the statistics for height. Okay. Then I'm plotting these ROC curves, response operator characteristic curve. And we've got some of these statistics that we saw in the tables above. I've put also just right here on the plot. This curve right here is called the ROC curve. We've got something called sensitivity on the y-axis and specificity on the x-axis, though I've flipped the axis on the down here. Notice we've got 0 on the right and it increases to 1 on the left. Perfect classification would be perfectly sensitive and perfectly specific. So that is a 1 and a 1. So that's a point in the top left corner. The best our model can do for a certain threshold, which we'll discuss in a moment, is at this circle here. That's the point that's closest to that top left corner. So that gives us a sensitivity right here of 0.768 and a specificity of 0.862, right, this line. Okay, so this is for handspan and this is for height. Height looks like it's a little bit closer to that corner, so that's already some indication that it's probably going to be a bit better. It does have higher sensitivity, but notice it does have lower specificity. Over here, the specificity was 862, but here on the right, it's closer to 0.8. It's 0.82. So it does better on one, but worse on the others. Classification is all about trade-offs. In fact, these two corners, the one up here, gives you perfect sensitivity, but a 0 specificity. Basically, you're predicting one of them perfect at the cost of the other. That's just like blindly saying that all people are female regardless of their height. That's what the corners, one of these corners says, and the other corners would be the opposite, like everyone's a male regardless of their height, that sort of thing. Okay. So first thing we need to do is learn about a lot of these terms. I started with 0 because ROC curve is just defining what this curve is, and then the rest are specific aspects that we learn from that curve. We are going to define all these terms by using Wikipedia links here, and then we are going to, for the key number 1 through 6 here, the key values here to interpret, I've already filled in the values for you. Oh, you're welcome. And then I'm going to have you discuss what it means in the context of our problem. So we've got these 6 to discuss, and then I need you to tell me which model you prefer and the evidence that supports that decision. Okay, so those are the 3 things we're going to do. We're going to define these terms, we're going to interpret them, and then we're going to decide which of these 2 models do we prefer. I'll just say right off the bat, these are both pretty good and pretty close to each other. Okay. All right, we're going to drill down on that in a moment. So let's start by, I'm going to just open these two tabs in new tabs. The confusion matrix stuff appears also. That's basically this big table right here. This is an overwhelming table. That appears again in the ROC article. You'll see if here's that gigantic table again. So let's actually start by looking at our data, and we'll come back here in just a moment. All right, perfect. Let's start here. Are all these sizes changing? Okay, that's sort of annoying. So, reference prediction. Let me just see if this is different. Reference prediction, yes. So, unfortunately, the horizontal axis in our table, the columns, and the rows are swapped in this table versus this table. But I think we can live with that. We'll just be very careful. Reference is the true value, whether someone identified as male or female when they took their measurements. Okay, so zeros are males, ones are females. Okay, prediction is what the model predicts them to be based on their hand span. Okay, so here's the males. The true males are zeros, and of those, 137 were predicted to be males. Those are correct, and 22 were incorrectly classified as females based on their hand span. Okay, so that's not too bad, right? It got most of them. Similarly, here's females. Of those females, 106 were correctly predicted to be females, and 32 were incorrectly predicted to be males. So again, pretty good, but the error rate was much higher for females in this scenario. All right, that is the main idea of the confusion matrix. You hope for large numbers on the diagonal because those are your correct classifications or predictions, and the off diagonals are where people are misclassified. All right, the rest of this has to do with our values calculated from these four numbers. If you can believe it, there's like 100 different numbers that you can calculate just based on four numbers. All right, so this is where I'm going to go over to here, the confusion matrix table, and think about this. Now, these rows and columns have been swapped. So we've got the actual condition. So now we've got the positives are the females. Okay, so this is like true females along rows, and true males are negatives. Okay, then we have what the model predicts, whether it correctly predicted a positive, right? So if someone was actually a positive and it was predicted as positive, that's a true positive. We did it. There's a bunch of additional words in here, and I'm only going to use the terms that I prefer to use. But some people call a true positive a hit, okay? But I'm going to ignore the other terminology. Depending on what discipline you are in, people have their own language for these things. Anyway, someone who's truly a female, they were predicted to be female, that's a true positive. Someone who is truly a female but was predicted to be a negative, a male, that is a false negative, right? We said it was a negative, but that's wrong because they're actually a positive. Okay, that's where that language comes from. If someone is a male, a negative, and they were predicted to be a negative, then they're a true negative. We got it right. But you can also have a false positive. That's when they were truly a negative, you predicted them to be a positive, but that's false. They're not a positive, they should have been a negative. So we have some of those terms. Terms that you've seen in hypothesis testing already has to do with type 1 error and type 2 error. So I just point that out, but not go into it. All right, let's make sure that we are defining the terms that we want to define. All right, so this is where you're going to start typing down here. Let's start by defining an ROC curve over in the ROC curve. Sorry, there we go. In the ROC curve Wikipedia page. Okay, so there's the same table. I'm going to scroll up to the top because that's probably where they're going to define ROC curve. An ROC curve, receiver operating characteristic curve. Actually, I don't know where that terminology comes from. I think it's something to do with engineering. Is a graphical plot that illustrates the diagnostic ability of a binary classifier system as to discrimination threshold, as its discrimination threshold is varied. So unfortunately, none of these plots sort of show you what's happening about the discrimination threshold. Let me go over to our plot and sort of walk through this. You can see down here, let's just look at handspan. We have a positive threshold greater than or equal to 0.472. That's this circle here. This curve is values that go from 0 to 1. Let's scroll up and look at this curve. Here's handspan on the x-axis, and here's the 0 to 1 probability of being female. Okay, when the probabilities, so we're basically trying to find a threshold, a horizontal line here that connects with this logistic curve. Okay, and so what did we say was like 0.4 something? So at 0.4 something, say it's right where my mouse is, you take a horizontal line and you intersect that curve. Boom. Everyone, or everywhere where this curve is greater than that threshold, you're going to consider a female. You're just going to classify them as female. And anywhere where the curve is less than that threshold, you're going to classify them as being a male. That's how simple it is. Now, because this only has one x variable, this ends up being very easy. When you draw a line horizontally to here, because this is a monotonic function, it's strictly decreasing, you can draw a line, draw a horizontal line over to the curve. Where it intersects, you draw a vertical line down, and you find a value of handspan. So let's just pretend it's not this, but let's just pretend that it's 21 centimeters, right? So anyone with a handspan of 21 centimeters or less is going to be classified as female, and everyone with 21 centimeters or greater, they will be classified as male. That's the basic idea. Okay. So that is, we vary. Now, we're going to need to define sensitivity and specificity to know whether the probability of 1 is in this corner or the probability of 1 is in this corner. But let's just say for a moment that it's in this top left corner. Then the probability of 1 is down here. As you decrease the probability, your sensitivity and specificity change until you get to this optimum value closest to the corner, and then you get down to the probability equals 0. So you're sweeping along the vertical axis, either from 0 to 1 or 1 to 0, and looking at all possible thresholds where if you're greater than that number, you classify as female. If you're less than that number, you classify as male. And you want to have some sort of criterion that says what is the best threshold here. Do I want to maximize the total sort of the accuracy in both groups, or do I want to make sure I'm classifying the females correctly and I'm willing to make errors for males, or vice versa? Okay, so depending on what you're trying to predict, you may have different goals. All right, so let's get into these definitions so that we can talk more specifically. All right, so the ROC curve is just this whole curve. All right, Now, we can calculate things from that curve. The next thing is going to be area under the curve. So let's look for AUC, area under the curve. And unfortunately, this page is not really written very well. I would have expected this to be defined somewhere else besides just starting with criticisms. But the area under the curve is, you can see this whole green area, which actually include the red area too. This is sort of a specific example, which we don't care about with the red square. But the area under the curve is just that. It's, if you've taken calculus, we often do integration, and that's area under the curve. And that area often means something. In this case, the area under the curve, there is a good sentence in here, using normalized. Okay, so there is a probabilistic interpretation of the area under the curve. When using normalized units, the area under the curve, which you often just say is AUC for area under curve, is equal to the probability that a classifier will rank a randomly chosen positive instance, that's like females, higher than a randomly chosen negative one, a female. So does our model just correctly predict the, random female versus random male? If you put them together, will your model predict the probability higher for female than male, right? If so, then your model is doing decent prediction. So that's one way of interpreting the area under the curve. In other words, when given one randomly selected positive instance, a female, and one randomly selected negative instance, male, the area under the curve is the probability that the classifier will be able to tell which one is which. Because if you swap those, then you've made an error, probably two errors. Okay. So, and they've got some math to show something. Okay, so that's the basic idea of the area under the curve. The bigger that curve is, or the bigger the area is, the better your classifier is. Notice I've got this diagonal line. Okay, that diagonal line is basically the coin flip example, where for any new observations you just randomly classify them as to male or female, and that is that the diagonal line is the ROC curve associated with that random coin flip. It's not a good predictor, right, because it's random. What else do we have for values here? So sensitivity, so now we're going to get specific as to like which one is correctly classifying males or females. So if we go back up to our table and we look for sensitivity, okay, sensitivity is the true positive rate. It is this ratio, so it's the number of true positives, TP, divided by the total number of positives. Okay, so of all the positives, what proportion did you get correct? So remember, our positives are females. That's our actual, right? So how many females did we correctly classify as females? That's going to be our sensitivity. So the higher that is, that's our y-axis here. So now we know that our y-axis is about predicting females. And actually, some of my comments here at the bottom help us remember that that's what's true. Here I've got classification labels. Number 1 is positive, 0 is negative. Sensitivity is the true positive rate. It's the probability of correctly classifying a 1 or a female. So this y-axis is the probability of correctly identifying a female. Similarly, specificity is the correct, well, let's go over to the definition. Specificity, let's see, we've got negative, here it is. It's the true negative rate. So we start with our true negatives. That's these. Oh, no, sorry. True negatives. So how many males did we correctly classify as negative males, divided by the total number of negatives, divided by the total number of males. So these are this ratio is the proportion of males correctly classified. That's the specificity. So if we go over here, the x-axis is the proportion of males correctly classified, and we want to be as close to 1 as possible. So just as a quick interpretation of this sensitivity and specificity between these two curves. Remember over here, we have pretty good sensitivity, right, 76%, and really, really good specificity, 86%. So we're correctly classifying females 76% and males 86%. But if we use height, we do better for females. We get up to 82%, but males go down from 86 down to 82%. Now, one thing that's really nice about this is that sensitivity and specificity are almost the same. So we are misclassifying the same amount, same proportion of males and females using this height model. Then the handspan predicts females better. No, excuse me, it predicts males better specificity, but we're not predicting females as well with handspan. So, so that you may use some of that in some of the interpretation below. Okay, I may not decide to repeat all that stuff. Okay, so that's specificity. Balanced accuracy. This is a statistic I use pretty commonly, even though there are slightly better ones, but it's an easy statistic to understand. It is the true positive rate, TPR, okay, true positive rate, that is the, excuse me, that's the wrong one, true positive rate, that's our sensitivity, okay, it's a plus our true negative rate was our specificity, right, so we know what both of those are. That's the proportion of females correctly classified, the proportion of males correctly classified, and we're just taking the average. So the average, right, is a balance. So overall, between males and females, like what is the average accuracy between these two groups? And it's not weighted by the people in our sample, right? So we could have 300 females and 100 males, and this is just taking the plain average of those two rates, those two proportions. Is not weighted by the number of people in our sample, because we don't care that much about the number of people in our sample. We care more about new observations that we're predicting for our population. So if our population is roughly balanced, but our sample is imbalanced, we still want to know what the balanced accuracy is. Okay. Now, if your population was imbalanced in terms of the groups, right? So, for example, I lived in New England when I grew up. Everyone was white. That was my experience. I had one black kid in my high school, which was a small high school, which was the only non-white person I knew through all of my schooling. Anyway, the proportion of the races are not equal up there, is my only point. Okay, so you sort of need maybe a different measure of accuracy in that scenario. Anyway, so that is what the balanced accuracy, it's the average of these two. All right, a couple other values which are helpful is the positive predictive value and the negative predictive value. So the positive predictive value is here. It is the true positive, okay, divided by the predicted positive. Okay, so we'll need to interpret that a little bit. So of all the people who we predicted to be positive, so our model predicted people into female or male groups, for all the people we predicted to be female, what proportion of those are truly female? Okay, that's the interpretation. So if you made a bunch of predictions, you want them to be right. And what proportion of your female predictions are truly female? That's what that is. And then similarly, the negative predictive value is the same thing, but for males, right? So of those people so the denominator here are the predictive negatives, So of those people you predicted to be males, how many did you predict correctly, the true negatives? Okay, so that is the positive predictive value and negative predictive value. The last number I have down here is just the threshold. I call it the positive threshold, but just to say sort of what direction it needs to be. So if everyone who's greater than 0.47 is going to be predicted as a positive, so meaning a female. So 0.47 on the curve, everything that's above that gets classified as being a female. All right. That number just comes from trying to get the place on this curve that is closest to the top left corner. Perfect sensitivity and specificity. All right. So having defined all those, we can make some comparisons about compare each of these statistics between the two models. So we've got, for example, the area under the curve is 0.859 for handspan and 0.901 for height. I calculate the difference here. I use handspan as the baseline model. So the value of difference is height minus handspan. So if this is positive, height is better. And if it's negative, then height is worse. I think all of these statistics, larger is better. We want all of them to be close to 1. Okay, so for area under the curve, let's see what we want to discuss here. So we want to discuss sort of their overall size and how much different they are, and whether that leads you to prefer one model over the other. All right. So in this case, they're both pretty high, close to about 90% area. Right. The area here, right? This is a unit square. The height is 1 unit. The width is 1 unit. So the maximum area is 1 squared unit. So that's the best you can do. This neutral diagonal is 1/2. So that's sort of the lowest you'd want to go for an area under the curve. There are prediction models that do worse than that, where you get this concave up type shape for your plot, and your model's done terribly. Fit a different model. Anyway, so both of ours are pretty large, and the difference is not that big. What is big and what's small here? So a lot of these can be thought about because they're on a 0 to 1 scale. You might think of them a little bit like probabilities. They're not all probabilities, but they are all proportions. So what is a large difference between two proportions? I would say maybe like 5% sort of starts to get a little bit big if something's 5% more than another. On the absolute scale from 0 to 1, then that starts to be pretty big. So anyway, I'll just give you that as a sort of a threshold of being big or not. So this I would say is somewhat moderately big. And so this gives us some preference for the model with the larger area under the curve. So this is sort of helps us think about height as being maybe a slightly better model, but not a lot better. For sensitivity, this is the ability to correctly classify females. We have 76% versus 82%. That's almost a 6% difference. That's quite a bit better. The height model was quite a bit better for helping to predict females. So that's the interpretation, and that is another more evidence for height being maybe a better predictor here. Specificity is the ability to correctly classify males, and we went down between the hand span and height models of about 4%. So you sort of have to think like, is it going to the height model from the handspan model female prediction increased to almost 6%, but male prediction decreased about 4%. Is that a good trade-off? And overall, I think we ended up predicting better. So we're going to see that in a moment for balanced accuracy. But you know, this is sort of a strike against the height model because it does worse for predicting males. So in this case, you know, it's a small difference or medium difference, and in favor of the handspan model, okay, for specificity. Balanced accuracy is this weighted, not weighted average, this strict average between correctly predicting females and correctly predicting males. It's slightly better for height by about 1%. So there's a very small improvement in prediction overall for both male and female if you use the height model versus the handspan model. Positive predictive value, these I think are not going to be quite as important, but sort of maybe interesting to think about. So of those who were predicted as being female, right, predicted as being female, how many were truly female? So of all of our female classifications, 82% versus 80%. So the height model does about 2.5% worse. And for males, negative predictive value for everyone who was predicted as being a male. What proportion were truly males? So we had 81 versus 84%, so a 3% difference. So the height model does slightly better in that scenario. So we've got, I think most of these differences are positive, and that leads us maybe to preferring the height model over the handspan model, but just by a little bit. Okay, so that I think is the overall summary. All right. Well, I will say that this was a very fun assignment to design and make for you. I hope you learned some of these terms through this and got a feel for what prediction looks like. You will probably see these types of curves in your career at some point whenever you do prediction. And if not, you might ask them, hey, do you have an ROC curve for your predictions? This is most commonly used for when you have a binary category that you are predicting. So in this case, just male and female and not other categories. But you can use ROC curves when you've got multiple categories as well. Instead of just one ROC curve, though, you will have multiple. You'll have, remember what I was saying about success and failure in terms of categories? Say you had 5 potential outcomes. You would have 5 separate ROC curves. You would choose one of the outcomes as being success and the other 4 is failure. And you would say, how well do I predict this success group versus all the others? That would be one ROC curve. Then you would take the second one and have that one be success and group the others as failures. And you'd have a second ROC curve. And you do that for each potential category that you are predicting. If you are predicting numeric variables, like in a multiple regression with a numeric y variable, ROC curve doesn't really apply there. It's only really for categories. Okay. Because you need categories to be able to calculate all this stuff. Things need to be in 2 categories. When you have a numeric scale, they don't fall neatly into these little boxes. Okay. There are other strategies for that. Okay, well, I hope that was interesting for you and that you learned something. Yeah, I think I covered everything just looking at my solutions. Okay, very good. Well, I hope you enjoyed the assignment, and I'll see you in the next one.